Hello everyone! In this video we will continue to examine uncertainty and error, topic 1.2, and in particular random and systematic errors. Alright, so in the last video we introduced random and systematic error as well as precision and accuracy. And I've touched on a bunch of what I'm about to say in the previous videos, but it's important to really understand sort of the relationship between these concepts. And they all come to a head when we discuss sort of how do we address error? So how do we deal with it as scientists? And it's pretty straightforward here. Random error is relatively straightforward to deal with as long as you account for it. The effects of random error can be reduced by taking more or multiple trials. So you, instead of taking a single measurement or even a couple measurements, you take more. And how many you need to take can be statistically sort of quantified relative to your error. But the general idea is the larger your random error, the more trials you need to take to converge on the right value. And with more data, the average of that data taken comes closer and closer to the true value, assuming no systematic error. Okay, random error can be measured carefully using statistics. So if you take enough data, you can quantify how much random error you have. And I gotta say, 9 times out of 10, when people sort of give you a value for their error, all they're giving you is the quantified random error. Okay, all they're giving you is the quantified error. So if you ever see a measurement given with sort of a plus or minus, that is almost always quantifying the random error in one way or another. Now, in this class, you'll be welcome to use what I'll call the range method for quantifying that error. We'll talk more about that as we go through sort of lab reports, and that's introduced. But the range method gives sort of the max minus the minimum value divided by 2. And it's basically saying, all right, if this is my measurement and this is the range, you take the max and the min, you divide it by 2, that's your error. It's a pretty rough mechanism for measuring the error, but it's fine for this class. More sophisticated ways of calculating that random error given sufficient data, so don't do this with only 3 trials, but if you have sort of 5 trials or more, you can quantify the standard deviation, or even better, the standard error on the mean. Don't worry about it. If you don't know what these things are, you're going to want to focus on this. Or you come talk to me about it. I'm happy to explain. So how do we address random error? We take more data. That's the big picture. Notice, I should be careful about here. Trial is a word that you're going to want to use correctly. A trial is a complete repetition of a single measurement. So let's say I'm measuring a bunch of different heights, and I'm timing the time it takes for a ball to drop. If I'm taking multiple trials, what that means is I'm taking multiple measurements of the same height. If I'm taking multiple heights, that's not a trial. That's a different value of the independent variable. So a trial has to be literally a repeat measurement. Okay? All right, so how do we address systematic error? Well, this is a good news and bad news situation. If the cause or the true value of the measurement is known, then the systematic error can be measured and subtracted out. So if for whatever reason you happen to know the actual value of what it is that you're trying to measure, you can measure that systematic error and subtract it out. That is, you can measure this sort of distance away from that true value and simply subtract that distance from every one of your values. You'll notice the problem with this is that it presumes you already know the true value. Okay, so what happens if you don't know the true value? Well, sometimes you know the cause of the error. So you identify, for example, that your ruler is short or that you didn't zero it properly. If that's the case, you can identify the cause, figure out how much error it would have introduced to each of your measurements, and subtract it out. That's an example where if you know sort of the full cause, you don't necessarily need to know the true value to subtract that systematic error out, okay? But the problem is, often neither of these things are true. So in real science, people are trying to measure values that have not been measured before. So they don't know what the true value is, and they don't know that they've made a mistake in their methodology or with their instrumentation. These errors are systematic errors, and they are impossible to account for, which is why when the error, quote unquote, is given in a scientific paper, often the only value that's given is random error, not systematic error, because if it were systematic, the scientists would have already accounted for it and subtracted out. So, strictly speaking, in sort of new science, or when you're doing research and you don't know what the value is supposed to be, it's impossible to directly account quantitatively for the systematic error if you don't know the cause. And that's pretty scary.